there, my name is June and welcome to another video of Learning with Levi. In this video, we'll be going over addition reactions. It'll be a two-part video, so stay tuned and make sure you hit the bell icon to get notified when the second part drops. We've also started doing a podcast format for those who'd like to reinforce the concepts on the go, and I'll link those down below. So here's what a general addition reaction looks like. Step 1, the double bond attacks the electrophile and forms a carbocation. Step 2, the nucleophile attacks the carbocation. Now, before we move any further, we have to define two things: Markovnikov and Anti-Markovnikov Rule. The Markovnikov Rule states that the hydrogen atoms in addition reactions are bonded to the carbon atom with more hydrogen substituents. Now, we can remember the Markovnikov Rule because it starts with an M and it bonds to the carbon atom with more hydrogen substituents. Now, if we look at the reaction in the middle, we have a general 2-carbon alkene. On the left of the double bond, we have an R group and 1 hydrogen. On the right, we have 2 hydrogens. Now, if we follow Markovnikov's rule, when we add the HBr, we add the hydrogen to the carbon atom with more hydrogen substituents, as seen in the red hydrogen. And for those listening, it would be added to the right side of the double bond, where the 2 hydrogens are. Doing so will give us a secondary carbocation. The nucleophile, and in this case would be the bromine, attacks the carbocation and forms the addition product. The Anti-Markovnikov Rule states that the hydrogen atom in the addition reaction are bonded to the carbon atom with the least hydrogen substituents. The first step is the formation of radicals, and that occurs through peroxide collections that have been exposed to air, which then produce radicals. The initial radical then reacts with the reactant, in this case HBr, to form another radical, which would be the bromine radical. The bromine radical then reacts with the alkene to form an allylic radical, and as a side note, when forming radical intermediates, the same rule applies as we did with carbocations. A tertiary carbocation is more stable than a secondary, in the same way that a tertiary radical is more stable than a secondary. The last step is the allylic radical, then abstracts a proton from the HBr to form the anti-Markovnikov product and then regenerate the radical. The last note is that in the addition of HBr in the presence of peroxides is only with HBr because radicals formed through HI, HCl, and HF are energetically unfavorable. Now again, if we look at this general 2-carbon alkene, on the left of the double bond we have an R group and 1 hydrogen. On the right side we have 2 hydrogens. Now if we follow Anti-Markovnikov Rule, when we add the HBr, we add the hydrogen atom to the carbon atom with less hydrogen substituents. And for those listening, it would be added to the left side of the double bond where the R and the hydrogen atom are. Now let's go over some addition reactions. The first one that we'll go over is the hydration of alkenes. In this reaction, the alkene reacts with water and an acidic catalyst to produce an alcohol. The first step is the protonation of the double bond by the acid and then the formation of the carbocation. A note here is that because the proton will be added to form the more stable carbocation, which then follows Markovnikov's rule, aka adding the proton to the carbon atom with more hydrogen substituents. Now be aware that because we form the carbocation, rearrangement will occur. The second step is water attacking the carbocation. The last step is the deprotonation of the water to give an alcohol on the more substituted carbon. The next reaction is the hydrogenation of alkenes. Notice that in this reaction we have PT, PD, and Ni listed. Those are platinum and palladium and nickel respectively. These are the metal catalysts used to help break the hydrogen-hydrogen bond. The hydrogen atoms are then placed to the metal catalyst, which are then ready to react with the alkene. As you can see, the addition of hydrogen atoms to the alkene produces a syn stereochemistry. The bottom portion, instead of using the metal catalyst, we can also use what's called a Wilkinson's catalyst to help with the hydrogenation of alkenes. The last thing that we want to mention is that the regiochemistry does not matter because we're adding the same group across the double bond. The next reaction that we have is dihydroxylation of alkenes. Now, if we ever wanted to add two OH groups to a double bond, this is how you do it. You can do it with Osminium Tetroxide, which is OSO4, or Potassium Permanganate, which is KMnO4. Now let's look at the Osminium Tetroxide first. The Osminium Tetroxide reacts with the alkene in a concerted manner to form a cyclic ester. Now, because of the concerted reaction, both carbon and oxygen bonds, which are shown in red, are formed at the same time, and then they're added to the same face of the double bond, and that explains why the stereochemistry is syn. Now, to hydrolyze the ester, we have to use peroxide, and we end up with a glycol, which is two alcohols, and then osminium tetroxide, which is regenerated to continue the hydroxylation of more alkenes. Now, if we look at the potassium permanganate, like the osminium, the cold permanganate reacts with the alkene in a concerted manner to form a cyclic ester. Now, the reason why it has to be cold is because if we were to have the permanganate warm, oxidative cleavage will occur. Now, because of the concerted reaction, both the carbon and oxygen bonds, which are shown in red, are formed at the same time, then they're added to the same face of the double bond, and again that explains why the stereochemistry is syn. To hydrolyze the ester this time, we have to use something basic like hydroxide, and then we end up with glycol, which again is two alcohols, and manganese dioxide, which is MnO2. Now, the last reaction that we have for this video is oxidative cleavage. Now, there are two ways that it can cleave the double bond. It's through permanganate and ozonolysis. So let's look at permanganate first. The first one you won't see as much because of, depending on one of the products, it can be oxidized. Now, if we look at the example of the alkene, there's two R groups on the left, and then left of the double bond, and then you have an R prime and a hydrogen on the right side of the double bond. If we add the warm potassium permanganate in an acidic solution, we see the oxidative cleavage gives us a ketone and an aldehyde product. However, the aldehyde can be further oxidized into carboxylic acid and eventually into CO2 and water. The other way to cleave a double bond is through ozonolysis. And ozone, which is O3, is used with DMS, which is dimethyl sulfide, which is a reducing agent to help cleave the double bond. Ozone reacts with the alkene to form a malozonide, which is then rearranges and it gets reduced by the dimethyl sulfide to obtain the product, which is a ketone and an aldehyde. Now, with that concludes the video. Hit that like button, subscribe button, support the channel, and share it with your friends who need help with organic chemistry. In the next video, we'll be going over the second part of the addition reactions. I'll be putting up more videos on organic chemistry, so let me know down below in the comments what you'd like to see. Social media links will also be down below, and as always, remember, you gotta go.